I would say not to focus too much on the definitions and anything else like that, but look at the examples, and especially look at the pictures. That can be useful in section 2.5. But the 2.5 homework itself, it's assigned, but I'm going to count that as extra credit. If you choose to do it, it's really up to you. Remember, all homework sections are 10 points, even though the point system is somewhat strange on the way it's listed on Canvas, right? I'll download the grades and then scale everything like it says on the syllabus to 10 points apiece for each of the sections, and that'll be the actual grades that are used in determining midterms and whatnot. So 2.5, the homework is available, but it will be extra credit. I encourage you to do it, but it's not obviously not required. And I even more encourage you to try to get the rest of all of Chapter 2 done as soon as possible. Along that same regards, saying that we're basically at the end of Chapter 2, that means that next week we should be looking at or thinking about having our Chapter 2 exam. My plan for that, on the other hand, is not so concrete, is a little bit up in the air. And this is where I want feedback from all of you. I had hoped that I would have been on campus by now. Unfortunately, because of everything that's going on with the pandemic across the United States, a number of things in my medical recovery have gotten slowed down or bogged down by things that aren't even happening here in Chicago, but are around us. But yeah, I don't want to get too much into the details, but pandemic has caused delays in many form, and for many people who aren't sick with COVID, it's caused delays at labs, delays for particular surgeries, things like that, in certain parts of the country, and there's a bit of a spillover even into places that aren't dealing with the pandemic to the same degree. So I'm not on campus, unfortunately, yet at this point. We're not able to come in. So thinking about the exam, next Friday is the day that I plan on having our Chapter 2 exam. On Monday, I'd really like for us to have a class discussion about what format we want that to take, whether or not we want to take it online or have a take-home exam. Right, if we do it online, it would be during the last 50 minutes of a class period. With that last 50 minutes, right, the reasoning why would be it would kind of mirror the other section, right? So that both sections would have the same length of time. It's kind of the standard way that I would do in-class exams is only use half of your class for an exam. For that very reason, so that there's equity across the two sections. If, on the other hand, right, we want to take home exam, that makes things a lot easier. Honestly, I would, at this point, given the complexities of a in-class exam, would prefer a take-home exam. But we can talk about this more on Monday. And I really want feedback from all of you on Monday so that I can get moving on the design of that. I already have kind of some take-home exams designed. The issue with the in-class exam becomes one of proctoring, right? I'm not, right now during the normal class period, I don't require you to have your cameras on. I don't require, right, to see what's going on in your background or what you're doing at your computer. I assume that if you've logged in and are here in class, that you're listening to me at the very least. Preferably, you're also watching as well, and you're paying attention because you're the one who's spending money on me being here. So that being said, if we did an in-class exam, the method of proctoring would need to be one that can work for everybody, but that would require something like cameras on and things like that. There's also like the lockdown browser, but I know that there are a number of issues that students have with that, and trying to do that in a constrained amount of time can also be a little bit challenging. we are missing not quite a third of the class today due to sports, and so I want to make sure that the student athletes as well get a chance to weigh in. So yeah, thank you for bringing that up again on Monday, Daniel. Because like I said, I really want it to be a full class discussion, but I know today the volleyball team is gone, the football team I believe is traveling, and I think that one of the tennis teams might be as well. And so it makes it I've received a large number of emails. I mean, in some sense, it makes it nice because it's all the student athletes all at the same time, rather than sporadically. But it's also means that today we're definitely. I don't want to say we're not going to do anything too serious, but because we are. I mean, we're having our class, but we might end a little bit early depending upon how things go. Well, basically, my plan for today, due to that, is just to finish up 2.4, finish up chapter 2, answer any questions that you all have, and that'll be it's kind of where we're at for today, and that keeps us on track with the other section. I mean, they didn't leave early or anything, but we finished up chapter 2 and then looked at some examples examples of problems or questions that they had from the homework, and then that was pretty much our day. So all of that being said, right? Let me ask the general statement again. And questions, comments, concerns, or other things before we move back into new content? Okay, I'll take that as a no. No hands raised, nobody turn off their mutes. So where we were at on Monday is we had gotten about halfway through section 2.4, right? And so I want to remind us of what we were looking at. Right? 2.4 was our section on continuity, and continuity is all about, or maybe not all about, but our definition for continuity was really based off of when can we use substitution to go through and solve a limit problem, right? And our substitution being just the method of plugging in that value c when I can evaluate the limit as x approaches c of f of x, when is it equal to f of c? Because we saw a number of examples in 2.3 where that was the case, right? And where our limit theory required us to do a lot of extra work that ended up, right, if we were just following the limit laws, to end up with just plugging a number in. And so we wanted this idea of knowing when can I plug a number in, when can I not just plug a number in, right? And that's where we got the idea of continuity and discontinuity, right? Or continuous and discontinuous, where that the limit, right, as x approaches c of a function f of x is equal to f of c, right? So I can plug a number in and plug in c to evaluate the limit, right? And if I can't do that, if that limit doesn't exist or those two things aren't equal, right, then we would say that that function is discontinuous. We then went and talked about one-sided continuity, so thinking about looking at these just from the left and just from the right, just like we did with limits, right, and how the general definition then of continuous can be broken down into left continuous and right continuous. And similarly, if I have both of the one-sided continuities, and it's important there that we had that both, right, then our function is continuous, right? So we can talk about the general form of continuity at a point by talking about the one-sided continuities at the point, right, in that relationship. And then oftentimes we're just going to look at functions really for most of the rest of the semester. If I just talk about a continuous function on a given domain, right, that just means that the function is continuous for all values inside of that given domain, right? And part of what we started to do in 2.4 was later towards the end was talk about what are some families or some classes of continuous functions and what are those domains. And so, right, oftentimes we're just talking about a function being continuous. And if I don't talk about a domain or a value C, right, this is really what I'm looking at here, where the domain is just implied. Followed that up then by going, how can a function be discontinuous, right? And so we said that there are 3 ways, or defined or gave ourselves 3 ways for continuity to break down, or for us to be discontinuous. One of those being a jump discontinuity, where the left-hand and right-hand limits aren't the same, right? And so, right, the mental picture that I always have with this, right, is, right, I'm video game character like Mario and Luigi working on an old screen scroller type video game, and to get from one part of the function to another at that value C, right, I have to jump up or jump down, right? I can't just keep walking along. It's not just like going up a hill. It's, right, there's a wall there or a cliff there. Right, the second kind of discontinuity that we could have was called a removable discontinuity, right? And my mental picture, once again, is a pothole for this one, right? As I'm driving along the road, I know what should be there, but a little piece of the road is missing, right? But I can go and fill that in relatively easily, right? That's right. I can call in the road crew, right? And they can put a little asphalt patch in the road if we need to, right? And those removable discontinuities, we worked a lot of examples in 2.3 that were actually that places where the value f of c either didn't exist or wasn't the same as the function. And most of the examples from 2.3 were places where those limits didn't exist. Right? Sorry, the limit existed, but the value of the function didn't exist. Let me see if I can find a good example that we had. Yeah, like any of these with the 0 over 0 indeterminate form are the types of problems that have those removable discontinuities, right? I was able to actually go through and evaluate the limit of this function, the t minus 9 over the square root of t minus 3, right? But this function isn't defined at 9, right? And so f of 9 doesn't exist, but the limit exists, right? And so in other words, this, right, if I had a function f of x that was t minus 9 divided by the square root of t minus 3, right? 9 wouldn't be in its domain. It wouldn't be defined at 9, but it would have a removable discontinuity there, and the function everywhere else pretty much looks like the square root of t plus 3. I mean, not pretty much, it looks like the square root of t plus 3, right? So if I knew what the graph of the square root of t plus 3 is, right, I'm able to go through and solve the limit problem, but, right, function isn't continuous there. So that's that important difference, right? Those examples where we got a limit out but couldn't actually plug a value in, right? Or those removable discontinuities. And then finally, the last type that we had for our classification was that infinite discontinuity, right? Where either the limit from the left or limit from the right, right, goes off to positive or negative infinity. At any place where we have a vertical asymptote, right? We say we have an infinite discontinuity. It's important, right? Once again, that I only need it to go to infinity on one side or the other for it to have an infinite discontinuity there. I don't need both. So I could talk about something like the natural log function, right, has an infinite discontinuity at 0, right, because it goes down to negative infinity, right, as the x values approach 0 from the right-hand side. It's not even defined on the left-hand side, though, right? Values less than 0 aren't in the domain, and actually 0 itself isn't in the domain of the natural log function. Okay, and so that's where we ended class on Monday. And so what we want to do is continue on with this a little bit and add a little bit more to it. So let me move that out of the way. There's that. Okay. All right, and so we're still in section 2.4. So let's call this. Right, just a reminder, right? 2.4, section 2.4 continued. Just for sake of the notes to remind us of where we're at. All right, so we looked at those classifications. Right now, what we want to do is say, what else can I do with, what else can I say about continuity, right? And so we're going to talk about laws of continuity. In other words, if I know something about some continuous functions, so let's suppose we have two functions. Right, so suppose that we have two functions f and g that are continuous, right, on ostensibly whatever our domain is that's given, right? Then we know that the following sets of functions are also continuous, right? So this is the sum difference. Right, and the constant multiple law, right? So the sum and difference law says that if I have the sum and difference of two continuous functions, it's also continuous, right? And the constant multiple law says if I have a continuous function, I multiply it by a constant, that function is also continuous, right? We've seen these before, right? These are our linearity laws. Right, I mentioned that term with limits, right? And the sum and difference law, right? The stuff about continuity really is directly derived from, or is a direct consequence, right, for the equivalent limit laws, right? And so the sum and difference law for limits really implies our sum and difference law for continuity, right? And our constant multiple law for limits directly implies the constant multiple law for continuity, right? We have some other functions as well that don't necessarily come as straightforward from, well, that are, I shouldn't say, that come from or apply to the taking those limit laws, right? But we can't necessarily take all the limit laws. I'm just going to take a few of them because some of them don't translate as nicely. In the continuity, we have more things to worry about than what we had with just straight limits. Right, and so the product of two continuous functions is continuous, and then the quotient law for continuity, right, says that we can look at the quotient and it's continuous, right, when g of x is not equal to 0. So as long as I'm not dividing by 0, right, I know that the quotient of two continuous functions is continuous. All right, now that really can be taken all the way back to some of the stuff that we looked at in 2.3, right? Because in 2.3, if you remember, right, we were talking about, I didn't at that point really call them continuous functions, but I said we give ourselves two families of functions that we could evaluate limits via substitution. And that was polynomial functions, right? We could do that for any real number, right? And since polynomials are the sum and difference of constants times powers of k, or sorry, constants k, words, difficult times. Okay. Since polynomials are the sum and difference of terms, right, where each term looks like a constant times x to some power, right? Constant multiple law and the sum and difference law allow us to really think about just x to some power, right? And x to some power is the product of x a bunch of times. And we had back in 2.2, right, the theorem that said that the function y equals x, right, that when we evaluate the limit at c of the function y equals x, so the limit as x approaches c of x was equal to c, it really just says that y equals x is continuous. And so the sum and difference law and the constant multiple law, those linearity laws really tell us that polynomials then are continuous for whole real numbers. So we can rephrase what we said back in 2.3. Right? Similarly, then if I apply the quotient law to two polynomials, right, rational functions, polynomials divided by polynomials, right? We said back in 2.3, I can evaluate those limits as long as I'm not looking at a place where I divide by 0, right? And now we can rephrase that as saying rational functions are continuous as long as the denominator is not 0. Okay, so we have a couple of more laws of continuity or related laws of continuity that are going to be useful to us and are helpful for us when solving limit problems. And I'm going to write these theorems, but I'm not going to go through and prove them. Okay, but we need to understand, or we'll have times when we're going to need to apply these principles, right? And so first one here is about continuity and inverse functions. Better the first way. Right, so if we have a continuous function on an interval I, so I don't necessarily know that I is the full domain of the function. We might have a restricted domain, right? I'll give an example of what I mean by that. Just a second. All right, so if I have a function that's continuous on an interval, right, whose range is R, and I know that the inverse exists on that interval, right, then I know that the inverse function is continuous on whatever the range was, right, so on R. So I want to remind us of two things. One of them is going to be an example related to an example. And the other one, before I even do the example, let's remind ourselves what inverse functions, how we define inverse functions. Let's do that off to the side, right? Inverse functions. All right, recall. All right, so we should have seen or should know this definition from, say, a pre-calculus class, right? We say f of x and g of x are inverse functions. If f of g of x is x and g of f of x is equal to x, right. In this case, right, g of x is f inverse of x, right? So that -1 is not like the multiplicative, right? It's not a negative exponent, right? When I write it like that, right? F to the -1 is saying that it's the inverse of the function f. And that means that if I use function composition, right, I know that f evaluated at f inverse of x is going to give me back x. And similarly, if I take f inverse and evaluate it at f of x, I'll get back whatever x is. All right, so an example of this right, is if I look at f of x, right, let's do a relatively easy one. Right, your book has some additional examples of this, and we'll work on later actually with some more when we get to exponential and logarithmic functions. We'll need to come back to this idea of continuity and inverse functions. But right, if I think about just a basic function like f of x is x squared, right, on the domain from 0 to infinity. Right now, the x squared function is not invertible, or the inverse doesn't exist everywhere. I have to kind of focus on one branch, right? Because I need to be a little bit careful with the square function, right? Because if I square a negative number, I get back a positive number. So like f of -2 and f of 2, right? They both square to be 4. Right? 2 squared and -2 squared are both 4. And if I want to know that f of g of x, so when I compose it with its inverse, I get back what I started with, right? I have to say, well, do I want to just work with the positive numbers or just the negative numbers? Right? I can't use both, because if I tried to use both, right, this wouldn't be well defined. I wouldn't know whether or not, right, I should get back the positive or negative version. Oftentimes we just focus on the positive one, right? Because, right, makes our life a little bit easier, and we're used to that idea of not being able to take square roots of negative numbers. So that's really why I picked just that interval from 0 to infinity. Right, so if we think about f of x as x squared on 0 to infinity, right? Right, so that's our I, our interval I. Right, then our range, right? Well, if I square 0, it's equal to 0, and as I square positive numbers, they stay positive and get bigger, right? So the range is also 0 to infinity. Hence the inverse function, which is our square root function, right, or x to the 1/2, right, is continuous on that range, right, from 0 to infinity. Right, so the continuity and inverse function theorem here allows us to then start talking about continuity of root functions. And so in this case here, right, I'm able to show that the square root function is continuous, right? For positive numbers, it has a domain of positive numbers, right? And once again, right, can't take the square roots of negative numbers, at least not yet, right? Not in calculus of a real variable. Since that's the case, right, I need to make sure that I'm focused just on those positive numbers, right? And once again, right, the square root function and the square function, well, if I take a number, I square it and then take its square root, right? As long as it's a positive number, I'm going to get back to itself. I could think about that in terms of function composition, right? Making sure that I kind of verify that these are inverses of each other, right? If I evaluate the square function at x to the 1/2, so I have x to the 1/2 and then square it, I know that exponents to exponents multiply, and 2 times a half is equal to 1, and x to the 1 is just x, right? Anything to the first power is just itself. And if I compose the other direction, so I plug f of x into the f inverse function, right? So I take x squared and then take a square root, right? Same idea with the exponents. I'm just multiplying in the other direction with my exponents. Still 2 times a half, 1/2 times 2, right? Both of those equal 1, and I just get back what I started with. Right, so it's a pretty straightforward and easy way to take our basic functions and give us something about continuity of our root functions. And then continuing with this theme of continuity and composition, right, let's take that one step further, right? Because we want to look at continuity and compositions not just with inverse functions, but we need to know how this works in generality so that we can really, by the end of chapter 3, I can write down almost any algebraic expression, and you'll be able to go through and take the derivative, right? And I can write down a lot of expressions, a lot of mathematical expressions using composition. So continuity and function composition. Okay, so our goal here, what we're really looking at or looking for is that, about this composition function and it being continuous at C, right? So that's what we're trying to figure out is how can I show if I have something that's a more complicated expression that involves function composition, right? How can I show that it's continuous at a particular value? And the answer is, well, let's look at the inside function. So let's look at that g of x. And I first need to know that it's continuous at x equals c. And then I also need to know that the outside function is continuous at whatever value I get when I plug c into the inner function. So I need that the outside function is continuous at x equals g of c. Right, and if I know both of those facts, right, then I get the function composition, right, the function f of g of x, right, is continuous at that value of c. All right, so I look at the inside function at c, the place that I'm kind of the x value that I'm focused on, right? But I look at the outside function, the outer function f of x, right, at the value I get out when I plug in g of c, or the inner function, right, the value I get out from evaluating the inner function at c. Both of those together, right, will then tell me that that function composition is continuous at c. So I'll come back to that in just a second. But before I come back and give us an example, all right, let's look at let's give ourselves some things to work with. Right. Let's look at a collection of continuous functions and their domains. So I'll put the domains in parentheses after after the functions. So we already mentioned earlier, right? We already mentioned earlier that polynomials, right? We had this in 2.3, as I said, right? We can rephrase something we stated back in 2.3, right? Then for polynomials, I can just evaluate the limits at whatever value c I'm looking at. So that's really just saying the polynomials are continuous, right? And they're continuous, right? With the domains being for all real numbers. Right, and then back in 2.3, we also said, right, that rational functions are continuous, right? But this was the case, right, where we had to worry about, right, so take a polynomial and divide it by a polynomial. Right, and this is continuous when q of x, right, when that denominator is not 0. Right, so as long as I'm not dividing by 0, I know that a rational function is continuous. Right? However, at the zeros of q, so places where q of x would cross the x-axis, if I was just looking at the graph of q, right, those are places where that rational function r of x is not continuous. Right? And we've seen examples in 2.3 and earlier in 2.4, right, where those can either be things like removable discontinuities, right, or they could also be infinite discontinuity. So we gotta have like vertical asymptotes at some of those points as well. It really depends upon the relationship between P and Q and what does it look like at common factors. Is there anything I can cancel that can tell us about the continuity and what type of discontinuity we have at a particular value C, where a rational function is not continuous. All right, so our earlier, right, 2 slides ago, right, when we were looking at continuity and inverse functions, it said, well, if I take polynomials or just even the basic functions like our root functions, sorry, our power functions, right, and look at their inverses, right, I know that those inverses are going to be continuous, and that's where we can have our root functions, right, and so I can think about things like, let's just call them that, root functions. Right, and so we have things like f of x is x to 1 over n, right? And in this, for these types of functions, we have to be a little bit careful, right? These are continuous for, that's right, positive numbers if n is even, and then all real numbers if n is odd, right? Because I can only take square roots of positive numbers, right? Square roots, fourth roots, and etc., right? Any even root, I can only do that for positive numbers. Right? Can't take square roots and negatives. But if I have odd roots, so like a cube root, right? I can take the cube root of a negative number. That's fine. It just gives me back a negative. And that's really because if I go back to the original function, right? If I think about its inverse, the cube function, well, if I cube a negative, I get back a negative, right? If I take a negative number to the 5th power, it still gives me back a negative number, right? On the other hand, if I take a negative number to an even power, it switches the sign and gives me back a positive number. So with those positive numbers, right, I have to restrict root functions to just being defined or just being continuous on the positive numbers. If I have a odd root, right, I know that the domain of that function is going to be all real numbers. Okay. Right, some functions that we haven't focused on too much yet. Right, we're going to look at our trig functions. Y is equal to sine x and cosine x, right? And these are continuous for all real numbers. And if I know when sine and cosine are continuous, then I can use the laws of continuity to tell me about the continuity of all the rest of my trig functions, right? Because I can define tangent as sine over cosine, right? I know then the tangent is continuous as long as cosine isn't 0, right? That's the quotient law for continuity. Similarly, I know that secant is 1 over cosine, and so, right, secant is continuous as long as cosine isn't 0, right? Cosecant is 1 over sine, and so cosecant is continuous as long as sine isn't 0. And I can define cotangent as cosine over sine, right? And so cotangent is continuous as long as sine isn't 0. Right, and so I use those laws for continuity to tell me about, right, the domains of continuity for all the rest of the trig functions. But as long as I know about sine and cosine, I can go through and derive that, right? And so I'm going to be given this for sine and cosine. Right? Like I said, we can derive that for then I just mentioned for all the rest of our trig functions. Some functions we haven't looked too much at before, right, are exponential functions. So I can think about y equals b to the x. Right? And I'm going to make some restrictions on here. Let's let b be bigger than 0, not equal to 1. Right? And an exponential function whose base is bigger than 0 and not 1, that's continuous for all real numbers. And these restrictions, right, one, making sure that b is a positive number, so that base is positive, right? I don't know if I plugged in a negative number, even what does a negative number mean to, I always say, what would, right, -3 to the pi mean? What exactly does that expression mean? Or even -1 to the pi, right? I have no idea what that expression even means mathematically at this point. We don't really have any tools to even talk about kind of abstract ideas like that. But we've seen, right, I know what 2 to the x looks like, or 3 to the x, or e to the x, right? As long as my base is a positive number, I'm good. I'm going to throw out the b equals 1 case for a couple of reasons. One, b to the x, or sorry, 1 to the x, well, 1 to any power is always just 1. And so when b equals 1, things aren't interesting. When b equals 1, though, we also don't have inverses. And so I'm going to use that theorem that I have about continuity and inverses to talk about logarithmic functions. Right. And so I can look at y is equal to log base b of x. So b is now the base of our logarithm. And I can't have base 1 logarithms because 1 to any power is 1. It's not, when b equals 1, it's not an invertible function. The exponential function isn't invertible. It doesn't make sense then for the logarithms. Right, and so we have that b is a positive number, our bases are positive, not equals 1, right? But these have a similar property to those positive roots, or sorry, the even roots, right, where they're only continuous for positive numbers. Right, that's strictly bigger than 0. Okay. So I mentioned, right, once I had some continuous functions, right, we can then go back, and that idea of function composition, right? All right, so example, right, let's look at h of x is e to the 2x plus the square root of x. This is continuous. As I can rewrite h of x as f of g of x, right, with f of x, my outside function being e to the x, right, which is continuous for all real numbers, right, and g of x is 2x plus the square root of x, right? 2x is continuous for all real numbers, but the square root is only positive numbers, right? And so this is continuous, right, for x bigger than or equal to 0. So f here, right, continuous. All reals, right, and this is continuous, right, when x is bigger than or equal to 0 because of that square root function. All right, so if I use function composition to break things down, right, I can take what I know about those continuous functions or these collection of continuous functions along with our laws of continuity to then determine the continuity or when a more complicated function is also continuous. Okay. Now, we're not quite done with 2.4 here, but I think this is a good place for us to stop for now and take a little bit of a break. We have just one topic left to finish up in chapter 2. Right, we need to look at the intermediate value theorem, and let's take a little bit of a break till like 1:40, and then we can come back and finish that off. Sound good?
Yeah, sounds good.
Okay. So I will see you all in a little over 5 minutes.